PES. Think of it as a way to shine a special light on something and almost instantly figure out what atoms are inside and, even cooler, what their electrons are up to.
That's a great way to put it, yeah.
Yeah.
If you ever wonder how scientists really figure out, what makes a new material tick, maybe for batteries or solar cells, PES is often one of the first tools they reach for. It's like getting a peek under the hood at the atomic level.
Right. And we've got a source here that really gets into the details, the basics of PES, the main types like XPS and UPS, the machinery, decoding the results, and where it's actually used.
Yeah, it covers a lot of ground.
So our mission for this deep dive is to pull out the really crucial bits, the fascinating stuff, and make PES feel, well, less like a textbook and more like something you can actually get a handle on. Okay, so basics first. Where do we start?
Well, it all comes back to the photoelectric effect. Einstein's big idea, right?
Yeah.
You shine light photons onto a material. If that light has enough energy.
It can actually knock an electron clean out of an atom.
Exactly. It ejects an electron.
And there's that famous equation, EK equals high ebb. Looks a bit scary maybe, but break it down for us.
Sure. EK is just the kinetic energy of that electron that got kicked out, how fast it's moving when it leaves. High is the energy of the photon, the light particle that hit it. We control that, so we know it.
Okay.
Ebb is the important one here, the binding energy. That's how tightly the atom was holding onto that electron before the light hit. And dphi, the work function, that's just a property of the instrument measuring things, so it's a known value we can account for.
So if we can measure how fast the electron comes out, EK, and we know the energy of the light we put in and that instrument constant, we can figure out IB, the binding energy.
Precisely. We measure EK very carefully, and that lets us calculate ebb. We work backwards to find out how tightly bound that electron was.
And that binding energy, that's the key, isn't it? Because it's like a unique signature.
Exactly. It acts like a fingerprint for each element. See a peak at a certain binding energy, you've got, say, carbon or oxygen or silicon.
Yeah.
But it's actually even smarter than just a fingerprint.
How so?
Because that binding energy isn't exactly the same for, say, all carbon atoms. It shifts just a tiny bit, depending on what that carbon atom is bonded to, its chemical environment.
I'm interesting. So if carbon is bonded to another carbon versus being double bonded to an oxygen, the binding energy of its core electrons will be slightly different.
That's what we call the chemical shift. It's incredibly sensitive. It lets us not just see that carbon is there, but what kind of carbon it is, chemically speaking. Is it part of an alcohol, an acid, a simple hydrocarbon?
Wow, okay. That's powerful. So XPS, X-ray photoelectron spectroscopy, that's where this really shines, right? Using X-rays.
And it's the workhorse for this kind of analysis, yeah. XPS uses soft X-rays, typically from sources like aluminum K-alpha or magnesium K-alpha. They have enough energy to knock out those inner shell core-level electrons we were talking about.
The ones deep inside the atom.
Right. And from the spectrum, the plot of electron counts versus binding energy we get. First, the elemental composition. We can see which elements are there, except for hydrogen and helium. They're too light.
Okay.
Second, we get that chemical state information from the chemical shifts, oxidation states, bonding types, all that detail. Third, by looking at the intensity of the peaks, how many electrons we detect, we can quantify things and figure out the empirical formula, the relative amounts of each element.
And you mentioned surfaces earlier. Is XPS mostly looking at the surface?
Oh, absolutely. It's very surface specific because those electrons getting kicked out can't travel very far inside the solid material before they lose energy or get scattered. So we're typically only getting information from the top, say, 1 to 10 nanometers.
Just a few atomic layers deep, then.
Pretty much, which is perfect if you care about the surface. Think about catalysts where reactions happen right on the surface, or thin films in electronics, coatings on materials, corrosion layers. XPS is ideal for that.
Okay, that makes a lot of sense. So XPS gives us core electron info, elements, chemical states, and it's surface sensitive. What about the other type you mentioned, UPS, ultraviolet photoelectron spectroscopy?
Right, UPS. The key difference is the light source. Instead of X-rays, we use ultraviolet light, usually from helium lamps like He or He2. This light has much lower energy than X-rays.
Lower energy light, so it interacts with different electrons.
Exactly. It doesn't have enough energy to kick out those tightly bound core electrons. Instead, UPS primarily probes the valence electrons.
The outermost ones, the ones involved in chemical bonds and determining electrical properties.
Precisely. So UPS doesn't tell you much about elemental composition directly, but it gives you incredibly detailed information about the electronic structure of those valence electrons, what we call the valence band structure.
And that tells you
It's crucial for understanding why a material behaves electronically the way it does. Is it a conductor, a semiconductor, an insulator? What are its optical properties?
Yeah.
UPS maps out the allowed energy levels for those crucial outer electrons. It's essential for studying semiconductors, metals, organic electronic material.
Okay. What else can UPS do?
It's really good for measuring the work function of the material itself, the minimum energy needed to pluck an electron right off the very surface. And for molecules, especially in the gas phase, UPS can actually resolve the energies of individual molecular orbitals.
So you get direct insight into the bonding between atoms in a molecule.
You do. It's fundamental information. And because the electrons ejected in UPS have even lower kinetic energy than in XTS, they can travel even less distance through the material.
Meaning UPS is even more surface sensitive than XPS.
That's right. Sometimes just the very top atomic layer or two. So if you're studying how molecules stick to a surface, like adsorption, or the very first stages of oxidation, UPS is incredibly powerful.
So XPS for core levels, elements, chemical states, sort of top few nanometers. UPS for valence levels, electronic structure, bonding, work function, and like the absolute top layer. They sound quite complementary.
They really are. Often researchers use both techniques on the same sample to get a more complete picture.
Okay, let's peek inside the machine itself. How does a PS instrument actually, do all this? What are the main parts?
Well, first, you obviously need the photon source.
Mm-hmm.
As we said, an X-ray tube for XPS, usually hitting an aluminum or magnesium target, or a UV lamp for UPS, often using helium gas.
Right.
Sometimes, for really high-end stuff, people use synchrotrons, huge facilities that produce incredibly bright and tunable light, X-rays or UV.
Okay, light source.
Then the light hits your sample, which sits inside a sample chamber. And this chamber has to be under ultra-high vacuum, UHV.
Why the vacuum?
Two main reasons. First, you don't want the electrons you're trying to measure bumping into air molecules on their way to the detector that would mess up their energy. Second, you want to keep the sample surface extremely clean. At atmospheric pressure, surfaces get covered in junk almost instantly. UHV keeps it pristine.
Makes sense. Got to keep things clean and clear the path for those electrons. What happens after an electron gets knocked out?
It travels towards the electron energy analyzer. This is really the heart of the instrument. A very common type is a hemispherical analyzer. It uses electric fields to bend the paths of the electrons.
Like a prism for electrons, but using electricity instead of glass.
Kind of, yeah. It's designed so that only electrons with a very specific kinetic energy can make it through the analyzer at any given setting. By scanning the electric field, you allow electrons of different kinetic energies through, one after the other.
So it sorts them by energy, and then...
Then they hit a detector, which simply counts how many electrons arrive with that specific energy. And finally, you have a data system that records the number of electrons detected at each kinetic energy setting, converts kinetic energy to binding energy using that equation we talked about, and plots it all out. That's your spectrum.
So light source, sample and vacuum, analyzer sorts by energy, detector counts them, computer plots it. Got it. Now, that spectrum, what does it actually look like? How do we read it?
Typically, it's a graph. The horizontal axis is binding energy, usually increasing from right to left, and the vertical axis is the intensity or the number of electrons detected.
And you see peaks.
You see peaks, yes. Each peak corresponds to electrons being ejected from a specific energy level in the atoms of your sample. In XPS, you'll see sharp peaks corresponding to the different core levels, like the carbon 1s, oxygen 1s, silic 2p levels, things like that. Their position tells you the element.
And the chemical shift tells you the bonding environment.
Exactly. In UPS, you typically see broader features rather than sharp peaks, representing the whole collection of energy levels in the valence band. Or, for gas phase molecules, you might see finer peaks corresponding to individual molecular orbitals.
And the height, or actually the area under the peak, tells you how much of that element or state is there.
That's right. The peak area is proportional to the concentration. We often have to apply something called sensitivity factors because some electron levels are just inherently easier to eject electrons from than others. But yes, intensity relates to quantity.
Does the shape of the peak matter too?
It can, yeah. Sometimes a peak might look asymmetric or broader than expected, which could mean the element exists in slightly different environments. And in XPS, you often see peaks split into two closely spaced components. That's called spin-orbit splitting, and it gives you more specific information about the electron orbital it came from.
You also mentioned Auger peaks earlier. What are those?
Ah, yes. Auger, pronounced OJ. Electron emission is a different secondary process that happens after a core electron is initially knocked out in XPS. An outer electron drops down to fill the core hole, and the energy release can kick out another outer electron, the auger electron. These show up in the XPS spectrum too, but at positions that depend only on the element's energy levels, not the incoming X-ray energy. They can provide complementary chemical information.
Okay, interesting. And Koopman's theorem, you mentioned that for UPS.
Right. Koopman's theorem is, let's say, a useful approximation, mostly for interpreting UPS spectra of molecules. It basically says that the measured binding energy of an electron from a specific molecular orbital is roughly equal to the negative of the calculated energy of that orbital from theory.
So it helps connect the experiment to theoretical calculations of molecular structure.
Yeah, it provides a bridge. It's not perfectly accurate because it ignores some electron interaction effects, but it's often a good starting point for assigning the features you see in a UPS spectrum to specific molecular orbitals.
Okay, so we have these incredibly detailed techniques, XPS and UPS, that tell us what elements are present, how they're bonded, their electronic structure. This sounds amazing for scientists, but let's connect it back. Why should our listeners really care about PS? What's the real-world impact?
Oh, it's huge, really. Think about technology. The chips in your phone, your computer, they rely on incredibly thin, precisely controlled layers of different materials. PES, especially XPS, is used constantly in semiconductor manufacturing for quality control, making sure those layers have the right composition and thickness.
Okay, so electronics manufacturing. What else?
Material science in general. Understanding how metals corrode XPS can analyze the oxide layers forming on the surface, developing better catalysts for, say, cleaner fuel production or making plastics more efficiently. PES helps figure out how the catalyst surface interacts with molecules.
So better materials, cleaner energy.
Definitely. Designing new polymers, analyzing battery materials to see why they degrade, characterizing the surfaces of biomedical implants to make sure they're compatible with the body. It's everywhere.
Nanotechnology, too, I imagine.
Absolutely critical there. When things get that small, the surface properties dominate. KES is essential for characterizing nanoparticles used in medicine, electronics, cosmetics, you name it. Even environmental science, identifying pollutants absorbed onto soil particles or atmospheric aerosols.
Wow. It really seems like any time the surface of a material matters or its fundamental electronic behavior is key, P is likely involved somewhere in the background, driving innovation or solving problems.
That's a pretty good summary, yeah. It provides that fundamental insight that allows us to engineer materials and processes more effectively.
And it's not like the field is standing still, right? Are there new developments making PES even more powerful?
Oh, for sure. It's a very active field. One major area is angle-resolved photoelectron spectroscopy, IRPs. This is mostly a UPS technique. Instead of just collecting all the electrons, you measure their energy and the angle at which they come off the sample.
And what does the angle tell you?
It tells you about the electron's momentum inside the crystal. This allows scientists to directly map out the electronic band structure, how electron energy depends on momentum. It's indispensable for understanding quantum materials, things like superconductors, topological insulators, the really cutting-edge stuff in condensed matter physics.
So getting an even deeper quantum mechanical picture, cool. What else?
There's HXPES hard X-ray photoelectron spectroscopy. It uses much higher energy X-rays than conventional XPS.
Which means?
The electrons knocked out have higher kinetic energy, so they can travel further through the material before escaping. This means HAXPES can probe much deeper, maybe tens or even hundreds of nanometers, instead of just a few. It lets you look at bulk properties or interfaces buried beneath surface layers.
Ah, so getting past the immediate surface. Useful.
Very. Then there's time-resolved, PES, TRPES. Here, you use incredibly short pulses of light femtoseconds, that's a millionth of a billionth of a second. Use one pulse to excite the material, like start a chemical reaction or excite electrons, and then a second, delayed pulse to probe what's happening with PEL.
Like taking snapshots of electrons in action.
Exactly. It lets you study ultra-fast electron dynamics, how energy flows in materials, how chemical bonds form and break on their natural timescales.
Incredible. Anything else?
One more I'll mention is PEM, photoemission electron microscopy. It basically combines P with microscopy. You use the photo-emitted electrons to form an image of the surface.
So you can see where the different elements or chemical states are located on the surface.
Precisely. You get chemical maps with resolutions down to tens of nanometers. You can see variations across the surface, identify specific features. It adds spatial information to the chemical and electronic information from PES.
Wow. So the toolkit is constantly expanding, getting deeper, faster, adding momentum information, adding spatial mapping. It's clearly a technique with a lot of ongoing development.
Absolutely. These advancements keep opening up new scientific questions we can answer and new technological problems we can tackle.
Well, this has been fascinating, a really great deep dive. I think the big takeaway for me is just how much information you can get about a material, what it's made of, how it's put together chemically, how its electrons behave, just by carefully measuring the energy of electrons kicked out by light.
It's a powerful concept, isn't it? And remembering the two main flavors, XPS, using X-rays for core levels, giving elemental and chemical state info, and UPS using UV for valence levels, revealing electronic structure and bonding, helps frame it. They offer complementary views.
Right. So maybe the next time you pick up your phone or look at a solar panel or even just wonder how they make coatings stick to things, you can think about PS. Consider how this ability to essentially see the hidden electronic world inside materials makes so much of our modern technology possible. And maybe ponder what kinds of future breakthroughs might come next as these techniques get even more sophisticated.
Well said. It underpins a surprising amount of science and technology.
Thanks for joining us for this deep dive.